Now. All right. So talking about this chapter, talking about attention. We've been in the process of distinguishing between voluntary attention. We've look at this for a while, but uh, take it away for a second. In the voluntary attention paradigm, does anyone remember what is the attentional cue typically? The attentional cue in voluntary attention paradigms. What is the attentional cue in voluntary attention paradigms? Can anyone remember what it typically is?
An arrow?
Yes, it is. It is an arrow, and you can see it right there. This is the attentional cue right here. It indicates to the participant, okay, now what you need to do, participant, is move your attention over there, please, or move your attention over there, please. And the participant is supposedly using something like free will, or they're consciously moving, voluntarily moving their attention based on the symbolic meaning of the arrow, either to the right or to the left. So this is just reviewing the voluntary attention paradigm. Then there's some preparatory interval or delay period, and then you measure the participant's behavioral and or neural response to the target that occurs some amount of time after the cue was originally presented. So sometimes neural response are measured during the preparatory interval. So this is when you're waiting for something, you're attending to one side of the world, but you're still waiting for the stimulus to occur. You can measure the brain response there. Here, you can measure a behavioral response to the target, but you can also measure a neural response to the target right here. So remind you that you can you can measure a neural response during the preparatory interval, or you can measure a neural response to the target as well. But you can only record a behavioral response once the target has actually been presented. So that's one nice thing about brain imaging is you can measure brain activity when the participant's just thinking something. They're just waiting for something to happen mentally, but they're not actually doing any outward behavior yet. Behavioral measures have to wait until the target is actually presented in the voluntary attention paradigm. So this is just briefly review this is kind of a complicated study, so I wanted to review the primary findings. I'll remind you that the ERP aspect of this, which is these two things. This is when electrophysiological responses are recorded relative to the onset of a stimulus, which is time point zero. By the way, what is time point zero? What does this represent? Like what happened at time point zero in this study?
The cue was presented.
Yep, the cue, the arrow was presented at time point zero. And we're measuring the neural response right here. This is the preparatory interval. At this dashed line right here, this is the presentation of the target. The ERP is when you're measuring the event-related potential, the electrical response. You're measuring voltage in response without using a Fourier analysis, without breaking down without breaking the electrical signal down into its different sinusoidal components. So the ERP right here is not using a Fourier analysis, and contrasting that with alpha down here. Alpha is one of the middle frequency bands that can be isolated when you do the Fourier analysis. Alpha is a middle frequency band. And I guess a couple more things. So please remember that everything on the left side, all this data over here, these are coming from this electrode in the left hemisphere. And over here, these data are coming from this electrode in the right hemisphere. And the most robust finding has to do with alpha amplitude. And you can see that here for the left hemisphere the left hemisphere electrode alpha amplitude, that when you're attending to the lower right, there is actually less alpha amplitude. So the left hemisphere, when you're attending to the right side of the world, the alpha amplitude is relatively smaller than when you're attending to the left side of the world. This seems a little bit weird because we think, the brain's contralaterally organized. Why would the brain signal in the left hemisphere be smaller when you're attending to the contralateral side of the world? And the key thing to understanding why this makes sense is that alpha amplitude, it kind of has like an inverse relationship to how engaged you are. When you're very, very engaged with the world, when you're very, very attentive, alpha amplitude tends to decrease. When you're kind of half asleep, when you're not really paying attention, when you're not waiting for anything to occur in the world, you're not paying attention, alpha amplitude actually tends to go up. So high alpha amplitude means you're zoning out, not paying attention. Low alpha amplitude means you're strongly engaged. And so in that perspective, the fact that in this left hemisphere we're seeing lower alpha amplitude in the when we're attending to the right side of the world makes sense. My left hemisphere processes the right side of the world primarily. I'm paying attention to this right side of the world. Therefore, it makes sense that the alpha amplitude would be reduced. And please notice that just the opposite is happening over here. This is the right hemisphere electrode. And the right hemisphere electrode, alpha amplitude is less when you're paying attention to the left side of the world. Once again, contralateral from the right hemisphere is the left side of the world. Alpha amplitude is less in the right hemisphere when you're paying attention to the left side of the world compared to when you're paying attention to the right side of the world. The alpha amplitude is generally higher. So this is a review. This is a hard study. Anyone have questions or comments about this study? All right. Here's where we left off, I believe. So it says these are idealized results. If you read the caption below here, and so I keep that in mind. These are data which are similar to what is observed in actual studies on attention, but it is just these are come from a review article. Trends in Cognitive Science is a review journal, and so they presented idealized data. So they kind of made up data and basically say these are what the ERP responses tend to look like in our studies on attention. But the specifics, this particular article and this particular graph right here, this is looking at event-related potential responses to the target. So in this study right here, this is during the preparatory interval. This right here, the main part of analysis in this study was the preparatory interval, which is right here. They're measuring the neural responses in the preparatory interval. Here's a set of these data represent these represent our neural response to the target right here. So the target in this study is this little block right here. So you're given, once again, a voluntary attention cue, tells you to pay attention to the left side of the world or right side of the world. And there's a delay period. In this study, they weren't caring about the neural response to the delay period. They're caring particularly what happens what is the neural response of the target, depending on whether the target is occurring in the visual field that we're paying attention to, or if the target occurs in the visual field that we are not paying attention to. How does the neural response of the target change depending on whether we are paying attention to it or not paying attention to it? So this is measuring the neural response to the target. And the general thing you see here, this is an event-related potential, an ERP response that is not Fourier analyzed. So we're just looking at raw ERP amplitude that has not been Fourier analyzed. The general thing you see, so all of this neural response right here is you're only seeing the neural response to targets presented in the left hemifield. So presumably this is a right hemisphere electrode. We're measuring a right hemisphere electrode for stimuli presented in the left hemifield. In some trials, the stimulus told you to pay attention to the right. Sometimes it told you to pay attention to the left. All those trials, when it was telling you to pay attention to the right, you were waiting for something to occur over here. But when the target actually occurred, it actually occurred where you're not paying attention to. So for those trials where you're paying attention to the right here, they're getting your neural response to when you're not paying attention to the target, which was presented in the left hemifield. Compared to attend left trials, in attend left trials, target tells you, the cue tells you that the target's going to occur over here, and then a second later or so, the target actually does occur over there. So in those trials, they're measuring your neural response to the target when you are paying attention to it, when you're actively attending to the target, contrasting it with those trials where you are attending to the right side, in which case when the target appeared over here, you were attending over here, not attending to the side of the space where the target is. And the general findings here is that ERP amplitude is bigger in response to the target when you are paying attention to it, which is not particularly surprising. When you're paying attention to something, your event-related potential response to it is larger. Please note that that's the opposite. With alpha amplitude, we basically found the exact opposite. Remember, when you're paying attention to something with alpha amplitude during the preparatory interval, it caused the alpha amplitude to decrease. Here, when we're looking at event-related potential responses, not Fourier analyzed responses that are occurring in response to the target, we find just the opposite, that the ERP amplitude The unfiltered, not Fourier analyzed ERP amplitudes are bigger. And that's what this black line is right here. Black line is bigger here for the attend left. That's when you're paying attention to the thing over here, compared to the attend right, which is the dotted line when you're not paying attention to this thing over here. The P1, the N1, the P2, doesn't look like the N2 is. So P1, these early event-related potential responses are bigger in response to when you're attending to where you're not. So what is time point 0 here? In this study, can anyone figure out what is time point 0? What happens at time point 0 here?
Is that when the object is presented?
Yes. Instead of it being, well, which object though?
That bar?
Yeah, the target. That object, yes, that bar is the target. So please note that in the previous study that we were just looking at, time point 0 was the presentation of the cue, and they were measuring the brain response during the preparatory interval. In this study, time point 0 was the presentation of the target, and they're looking at neural activity in response to the target. One last thing about this graph is just knowing what these P1, N1, and P2. For those of you that are going to take more psychophysiology classes or deal more with ERPs, this lingo or this way of this naming scheme is very common in ERP studies. And the P and the N are easy to understand. P stands for positivity. And by the way, one thing about ERP studies that makes them a little hard to read the graphs sometimes is you notice how here positive is down and negative is up. In about half the studies, you'll see that, maybe even more than half, where positive is down, negative is up. So that's something to keep in mind. But this P stands for positivity, and this N stands for negativity. Each of the numbers, 1 and 2, represents the number of peaks, of positive and negative peaks that have occurred since the 0 time point. So P1 is called P1 because it's a positivity, and the 1 is because it's the first positive peak that occurs after the presentation of the target right here. So P1, peak number 1, positive peak number 1. N1 gets its name because it's a negativity, and it's the first negative peak after the target was presented. P2 is a positive peak, but it's the second positive peak that occurs after the presentation of the target. So all of these three, these are considered early event-related potentials, early in the sense that the stimulus is presented, and within 100 milliseconds, we're getting an event-related potential, the P1 right there. So these are all three of these ERP responses occurring within about 200 to 300 milliseconds of the target being presented. And the amplitude of each of these three responses is bigger when you're paying attention to the target compared to when you're not paying attention to the target. Any questions or comments about these findings? Yeah, these two ERP findings are challenging, but they're very, very representative of the types of ERP studies that exist. And there's some of the studies where ERPs are most useful at studying attention. Okay, reflexive attention now. We're done with voluntary attention. Voluntary attention, the cue was an arrow pointing to the left or right. In reflexive attention, the cue is something which grabs, it steals your attention. Contrasting that with an arrow is like you see the arrow, you're like, okay, I will consciously move my attention now over here. You're using your free will and the voluntary attention to move your attention to the left or right. In reflexive attention, you're not using your free will because your attention is kind of stolen from you by something which is attention grabbing, or yeah, that's the best word I can come up on the fly. Something that kind of grabs your attention because it's very salient, or maybe it kind of comes out of the blue, or it's louder than you were expecting. So here's an example from published literature where, once again, you're a participant and you're fixating here. And it's a covert attention task because you're either going to be paying attention with your peripheral vision over here or over here as a result of this cue right here. So the cue is like these little 4 dots that appear right around the point in space where they want you to pay attention. It's like a little flash of light. It's something that kind of gets your attention. It's kind of the equivalent of like when someone's trying to get your attention and they're doing this and they're moving their hands. It's kind of what's going on over here. The dots kind of briefly appear over here. They weren't there, and all of a sudden they flash. And the idea is that's pulling your attention over to the side of the world where that salient thing just happened. The light flashes, your attention is kind of reflexively pulled over to that side of the world. So the cue here, if I ask you on the test, what is the cue in the reflexive attention task? It would be like the sudden appearance of an object that quickly flashes and then disappears. In this case, these 4 circles which surround this point in space. So then there's a preparatory interval, a delay right here. Here they call it the interstimulus interval. So that's 3 different words for the same thing. Delay period, preparatory interval, interstimulus interval, basically all mean the same thing. They're the amount of time that occurs after the cue is presented and the target is presented. And in this study, one of the things they manipulated was the interstimulus interval, the amount of time from which the cue was presented to the target, and it ranged somewhere between 50 and 250 milliseconds. Sometimes the cue occurred, and then 50 milliseconds later, the target would occur. Sometimes the cue would occur, and then 250 milliseconds later, the target would occur. The target is this thing right here, like a checkerboard pattern, and I guess the task is something like when the checkerboard pattern appears on the screen, press some button on the keyboard as fast as you can. So this would be an example of a valid trial, because the cue tells you, okay, pay attention. The cue is pulling your attention to the left hemifield. Then there's a delay, and then the target occurs, and then here, the target is occurring in your left hemifield. On some trials, the cue would direct your attention over to the left hemifield, but then the target would occur in the right hemifield. So that would be like an invalid trial. It's reflexing attention is pulling you to one side of the world, but the actual target that they're measuring your behavioral or neural response to is in the other hemifield. So here is an event-related potential study in response to the target in the reflexive cueing paradigm. So once again, these are ERP, so these data are not Fourier analyzed. We're not looking at alpha amplitude, delta, we're just looking at raw EEG, raw electrical activity without filtering it or analyzing it in the various Fourier sinusoidal components. So the thing which is zoomed in here, the important event-related potential in this study is the P1. Once again, that P stands for positivity. The 1 represents the first peak that occurs in this study in response to the target, which is the 0 time point right here. So this study kind of adds a wrinkle into this idea. In the previous studies that we had talked about, we basically said, if the target is presented in the hemifield that you're paying attention to, in general, and I'll show you the data right here, in general, the ERP amplitudes are bigger. When we're measuring the ERP amplitudes, this is the voluntary attention paradigm. Basically what happens is that when you're paying attention to the target, it causes your event-related potential amplitudes to be bigger. There's a little bit of a wrinkle here in this study, and the reason is because they varied interstimulus interval, ISI, which I showed you about. That's this thing right here, interstimulus interval. It ranged between 50 and 250 milliseconds. So here's like a short one, like on the line of 50 milliseconds. Here's a longer interstimulus interval along the lines of like 250 milliseconds. So they broke things up into, is the preparatory interval, interstimulus interval, is it a short amount of time, 50 milliseconds, or a long amount of time, like 250 milliseconds. And what's interesting is they found that the neural attentional effect differs depending on the amount of time that it elapses between the attentional cue, which grabs your attention, and the presentation of the target. So cued basically means, the blue one, which is the same blue thing you see here, basically is when you're paying attention to the target. So this is like analogous to valid trials. The attentional cue pulls your attention to one direction, and then the target occurs sometime later in the same direction. Uncued is like equivalent of an invalid trial or a not valid trial. The attentional cue tells you it pulls your attention to one side of the hemifield, but the target ends up occurring on the opposite hemifield. And what they find, at least in this study, is that when there's a short interstimulus interval, the ERP amplitudes for the P1 tends to be bigger in the cued condition. That is when you're paying attention to the object. The cue occurs over here. The object occurs just 50 milliseconds later. The net result is basically your P1 amplitude is bigger in the attended condition when there's that short interstimulus interval between the cue and the target, 50 milliseconds. This seems to have a facilitatory effect on your neural processing, but only for 50 milliseconds. Because if you look at this condition right here, this is when the interstimulus interval is longer, 250 milliseconds. And here you actually see just the opposite. Here you actually see that the P1 amplitude is actually less when you're paying attention. So the cue occurs over here, but then there's a delay of 250 milliseconds. 250 milliseconds later, your processing of the target is actually worse in the attended condition, the cued condition, the valid condition, compared to the uncued, like the invalid condition. And so this is a little bit weird because here it actually suggests that our neural response is diminished when we're paying attention to the object. The cue tells us to pay attention to the same object, and 250 milliseconds later, the target occurs, and our neural response to it has actually been reduced compared to when the object was actually in the other hemifield that we're not paying attention to at all. So this is this in particular is the surprising finding. The short ISI one, that's not surprising. But here it is surprising because you actually find that the object which is in the attended hemifield, the neural response is actually smaller than the object which is in the not attended hemifield. This illustrates this concept which is talked about in the textbook, inhibition of return. I say here that it's reflexive attentional cueing effects are short-lived, and that's what we just demonstrated, though this actually applies to voluntary attention as well. The only study that I have data for is this reflexive attention study, but this idea of inhibition of return in theory also applies to voluntary attention studies. So an analogous effect does occur on reaction times. So the analogous effect in reaction times is when there's a short ISI and the target occurs in the hemifield that you are cued, your reaction times are really fast. Over here, when there's a long interstimulus interval, the cue occurs, and if the object occurs in the cued hemifield 250 milliseconds later, you're actually slower to respond than if the object is in the uncued hemifield. So once again, that's some interesting kind of counterintuitive data about long ISI here, which illustrates this idea of inhibition of return. Any questions or comments about any of the, we talked about like 3 or 4 different electrophysiological studies of attention, measuring neural responses during the preparatory interval in one study, and then response to the target in 2 or 3 different studies. Anyone have questions or comments about any of those before we move away from those? Let me look at you, make sure people are still alive out there. Yep, looks like we're still there. Okay. So let's move on. Okay, so at least for a little bit, we're kind of done talking about some of those. The ERP studies, they can be tricky. There's a lot going on in those event-related potential studies. So for a little bit, we'll take a break from those kind of dense ERP studies and talk about some neat behavioral findings that are related to attention. So unilateral spatial neglect is basically this idea that there are some individuals that have hard time paying attention to one side of space. They neglect one side of space and tend to pay attention to only half of space. They ignore the other half. So some interesting things about unilateral spatial neglect is that it's way more likely to occur after a right hemisphere lesion. You can have left hemisphere lesions and it does not tend to cause the same effect. So unilateral spatial neglect occurs very frequently after right hemisphere lesions, but it doesn't occur that you can have the same damage in the left hemisphere and it's not very likely to cause spatial neglect. So that's a little puzzle about the brain. So you can see spatial neglect in a right hemisphere person with a lesion to the right hemisphere, looking at things like any of these examples. Like here, a right hemisphere patient was told to draw a clock, and you can see that they neglected to draw the left side of the clock. So it's like when they were looking at the clock to draw, or the clock that they just drew, they were looking at the thing and somehow they forgot, they were not paying attention to the clock, so they didn't realize that they had not drawn the numbers 8 through 11. So they had not drawn the numbers 8 through 11, the left side of the clock, presumably because they were neglecting the left side of the world. Right hemisphere stroke tends to cause contralateral neglect, that is neglect of the left hemifield. Here's another example. The participant was asked to draw this scene right here. And there's several pieces of evidence that they were missing the left side of the scene. Once again, the stuff on the left side of the scene, like these 2 trees, they didn't draw them at all. On the house that they did kind of draw, they forgot to draw the left side of the house. And it might also be relevant that the trees they drew, the left side is a little bit like, trees usually think as being symmetrical. Like up here, the trees are mostly symmetrical. The left side is even a little bigger over here than it is over here, like this tree right here. But if you actually look at the way these trees are drawn, the left side is smaller than the right side. So it even seems like within each tree, they're tending to pay attention to the right side of the tree, and they tend to ignore the left side of the tree. So there's like 2 or 3 different things about this drawing right here that suggest that the patient with neglect was ignoring the left hemifield. Similar findings here. Draw this cat, and then here is the cat that the participant draw. Once again, they basically neglected to draw the left side of the body of the cat. So various examples. An individual with right hemisphere lesion has visual neglect, the inability to pay attention to the left hemifield. So here's another cool example of behavioral demonstration of an individual that has right hemisphere lesions. The task is to bisect these lines, called the line bisection task. Bisect means put a vertical line as close to the center of the horizontal line as you can. So I'm trying to do that right now, trying to put my mouse right through the center. And I believe I'm doing pretty good at it because both my hemispheres are intact, and I should be able to find the center of these lines no problem. But if you look at what the person does, this is the participant with right hemisphere lesion. There's a couple pieces of evidence, once again, that this individual is ignoring the left side of space. First of all, you can see that the individual apparently didn't even notice these 2 horizontal lines right here. And so the participant did not even attempt to draw vertical lines through these, suggesting that he neglected the whole left side of the array. But then when you look at each individual line, the participant shows evidence that they were neglecting the left side of the line. And the evidence comes from the fact that if you look at where the bisections occurred, they tended to occur far to the right of the line. Like this is not centered. This is clearly offset to the right. This is offset to the right. This one in particular is very offset to the right. The correct answer here would be more like over here. But this participant with right hemisphere damage was putting the line way over here. So the typical explanation for this is the participant is not paying attention to this side of the object. So they're only seeing a small fraction of the object. And so they put their vertical line through the middle of that small fraction of the object that they're processing, which makes their line go offset to the right. So anyone questions about so far these examples of visual neglect that we've talked about, these attentional blindness studies?
I have a curiosity question. So when they draw it, they don't draw the left part of the cat, for example. But when they see a cat, do they see the left side of the cat?
Well, you're saying the word see.
Like if they see an animal, are they going to see the left side of the animal?
I mean, it seems like, okay, the way I think about this is they probably see both the left sides and the right sides of the world, but they probably are paying way, way more attention to the right side of the world than the left. It's not like an all or nothing thing. So you asked, are they seeing the left side of the world? And I think that's kind of it's not like, yes, do they see it, or no, do they see it? It's how much time are they spend, or how much mental resources are they using to process it or pay attention to it? And my understanding is that people with neglect, they pay way less attention to what's going on the left side of the world than the right. So yeah, I think they see it, but they see it less than they see the stuff in the right hemifield. Yeah.
Has this only been observed with people who have suffered damage to their right hemisphere? Has it been seen in people with like damage to their left hemisphere as well?
Some people with damage to the left hemisphere have visual neglect effects, but it's significantly less. There's something about the right hemisphere where you get stronger contralateral neglect effects than in the left hemisphere. So, a small proportion of individuals with hemispheres in the left with lesions in the left hemisphere, they'll actually show the opposite pattern. So a very small percentage of people with left hemisphere damage will bisect the line over here. So they will show a very small percentage will show neglect of the right hemifield, but it's the percentage of individuals that show neglect after left hemisphere damage is way smaller than the percentage of individuals that will do it with right hemisphere damage.
One more question. Where actually is the lesions on the right hemisphere?
Well, it can vary. Usually the parietal lobe. Usually the parietal lobe would be my understanding of the area which most studies have shown are connected to these contralaterality effects, though you probably could find contralaterality effects in the visual cortices as well. So I would guess it's not just a single brain region. There's a network of brain regions which are processing the contralateral hemisphere, or the contralateral hemifield rather, and it most likely occurs the occipital lobe and the parietal lobe, maybe the frontal lobe. So a lot of brain regions are processing the contralateral side of the world, though the ones that I think have most clearly been connected to this contralateral processing would be occipital and parietal. Any other questions? Okay, here's one more example of neglect. So this is a study. What's cool about this is they're using they're measuring where people are looking. So they're showing people a picture on a screen, and then they're using an eye tracker, and the eye tracker measures wherever your eyes move. The eye tracker is basically measuring exactly where you're looking on the computer screen. It's a part of the computer which is looking at the participant and tracking their eyes, and it's coordinated to where exactly on the computer screen is the participant looking at any given point in time. And this is an individual with neglect compared to a control. And the individuals with neglect, once again, almost always occurs after right hemisphere lesion. The individuals with the neglect spend less time looking in the left hemifield than the right. They spend a lot of time looking over for some target over here, even if the target's not over here. The target's over here, they miss the target often, and they spend very little time even searching for it over here. So it's as though the left side of the world doesn't exist, as evidenced by the fact that they spend very small amounts of time looking at that side of the computer screen, that hemifield, compared to controls, which spend about equal amounts of time looking at both hemifields because both of their hemispheres are intact. So here's a cool idea that there's lots of, this is like a kind of a theme which reappears in this chapter, this idea of competition, attentional competition, and how neglect becomes much more apparent when there's noise in the environment or competing stimuli in the environment, which is illustrated nicely here in this study. So I'll repeat the basic punchline though. The study we're about to talk about here basically illustrates the idea that when there's a lot of things going on in the environment, when there's a lot of noise or where there's a lot of potentially distracting things in the environment, contralateral neglect becomes more pronounced. The effects become more severe when it's in a cluttered environment where there's lots of competition, lots of things vying, trying to steal your attention. And so this illustrates it here. So this is an individual, the guy right here has right hemisphere damage, presumably. So this guy you oftentimes will show left hemifield neglect where he cannot process things in the left hemifield. However, in this study, the researcher is doing this, and they're saying, tell me when you see my moving hand. Tell me when you see the target, which is my moving hand. And this individual, you can see, he says, yeah, you're doing it right there. You're doing it with that hand right there. And he's able to, if you think about his perspective, he is looking into his left hemifield. So what he's doing right here is he's actually demonstrating that in this particular situation, he is not demonstrating neglect. He has right hemisphere damage, but in this particular situation, he is able to find the target which is occurring in the left hemifield. The reason is because in this particular condition, there is less competition. There is less things in the environment that can distract him. Comparing it to, well, in this condition right here, this is not surprising at all. The participant is, once again, the lady's doing this now. She's saying, okay, so point to the target, which the target is my moving hand. Where's the target? And the participant can say, yeah, it's over there. It's in my right visual field. But that's not surprising, as we said, because it's very rare that you're going to see a person who neglects the right visual field. If you see neglect, most of the time, the person's neglecting the left hemifield. So this finding's a little bit surprising because this individual has right hemisphere damage is actually showing no signs of neglect right here. He's able to see the things in his right hemifield, which that's just not surprising at all. What's a little bit surprising here, though, is that in this condition, the lady's like, okay, where's the target? But it's kind of a trick question because the target, the moving hand, is actually in both visual fields. And so this provides, the participant has to give a response. Where is the target? He can say, you know, it's actually in both hemifields, but the participant is strongly biased in this situation to say, I only see one target and it's in my right visual field. So he can see, okay, I'm looking at a target and I see the one that's in my right visual field, but he doesn't notice the target that's in the left visual field. Over here, he was able to see the target in the left visual field, but that's because in that situation, only one of the targets was moving. There was not very much competition. There was not very much distraction. But here in condition C, there's more distraction. There's two things going on. It's just more complicated scene. And in that situation, the right hemisphere, which is damaged, that's when the neglect comes into, that's when the neglect becomes apparent. When there's two things going on, the participant is no longer able to process the stuff in the left visual field. He could process it over here, but when there's two things going on, it's like whatever's occurring in the right visual field that's stealing his attention. The left hemisphere is winning over. And so the stuff in the right visual field is getting processed kind of at the cost at the left hemifield. It's like this stuff over here is stealing my attention, which makes it so I can no longer deploy my attention back over here to the left visual field, the left hemifield. So the effect of neglect here only comes when we have competition. The thing, this is a term from your textbook, by the way, extinction. The thing that is being extinguished, the thing is becoming extinct, is the ability to process the left visual field. You can process the left visual field when there's no distractions, but once there's a distraction, you know, there's multiple things going on, the ability to process the left visual field is diminished. I'm going to have a harder time processing it. Any questions or comments? Okay, what do we got left? Yeah, we got it. Yeah, we'll probably be doing finishing up chapter 7 next time. Let's do vigilance, and then we'll probably call it vigilance and maybe one more fMRI study. Okay, so vigilance. This is a topic which is talked about a little bit in your book, but vigilance is actually a point which is mentioned a lot in the Master and His Emissary. And so I'm going to talk about vigilance and remind us of some of the findings from the Master's and Emissary, and I'm going to bring them into the lecture slides. So just to kind of defining vigilance, McGilchrist talks about vigilance being open. This is a common way of kind of thinking about vigilance. It's like open attention, waiting for something to potentially occur. And this is, McGilchrist also emphasized the fact that vigilance is something which is potentially important for detecting threats. So for like, you know, animals out in nature, threats would usually be like a predator. So the idea is that like when I'm in my house as an animal, when I'm in my cave or whatever, I don't need to be using a lot of attentional resources looking out for predators because I'm in a well-hidden place, which I'm kind of safe and hidden and protected inside my fort or inside my house. But when I go out in nature and I'm hunting or something, or I'm looking for berries or whatever, my vigilance will tend to be higher. I'll be using mental resources to try and find food, but I'll also be using mental resources to kind of keep my peripheral vision open for a potential threat that will cause me to have to hide or run and climb into a tree or run away or something like that. So this is the idea of vigilant attention. So I'm going to give an example of some findings from Master and His Emissary, but first I thought I would share with you some of these basic findings regarding vigilance in human beings. So some of this research initiated back for like World War II, when they were, you know, one important job is radar detection. When you're looking at the radar, you're on some type of a boat, and you're looking at the radar, and the radar is looking to see if there are enemy planes or maybe other enemy ships that are in the area. And it's a job where you're just kind of waiting, looking at the radar, processing the radar, waiting for a potential threat to occur. And obviously, as a radar detector, it's important that you be as quick as possible. And so they've done some research about how long can people use their vigilant attention to perform radar detection type tasks well. And the idea is that you can perform vigilant attention. You can maintain vigilant attention for about 15 to 30 minutes. But after about 30 minutes, that's kind of the peak, there's a pretty notable drop off in your ability to kind of keep that open vigilant attention waiting for predators, such that if a predator does occur, your reaction times to respond to it will be diminished. So for 15 to 30 minutes, your reaction times for predators are quick. But after about that, it's like your brain is getting fatigued potentially. Your ability to maintain that type of attention is not as strong, and the reaction times to respond to a threat slows down after about 30 minutes. Neurally, there's been some studies on the neural correlates of good versus bad vigilant attention, like when you are performing well versus when you're performing not well. And in general, theta, which is considered a low frequency, theta is Fourier analyzed, part of the EEG signal. It's a relatively low frequency sinusoidal component, and it negatively correlates with performance, meaning that in a vigilance task, people whose reaction times are very, very quick will tend to have they'll tend to have low theta amplitude. So if you're performing well, your theta amplitude will tend to be small. Yes, so performance gets better, your theta amplitude tends to get smaller. I'll say that one more time, as performance gets better, your theta amplitude tends to be smaller. That's a low frequency component. Beta amplitude is a high frequency component, and when you're performing really well in the vigilance task, when you're able to detect all the ships, you're able to detect them well. Beta amplitude, which is a high frequency component, it correlates positively, which means as your vigilance performance gets better, it's likely that your high amplitude response will also increase in amplitude as well. The high frequency response, rather, will increase in amplitude when you're performing well. So I think I need to repeat these. Theta amplitude is big when you're performing poorly in a vigilance task. Beta amplitude, which is a high frequency component, is high. Is the amplitude of beta frequency amplitude is high when you're doing well in a vigilance task. And so, yeah, one more thing I want to mention about vigilance in general is that this 15 to 30 minute idea, I can always think of an idea every summer when I'm at a certain recreational activity, and I noticed that one of the individuals there who works at this place, the individuals are changing, they're rotating so that a new person is doing this job every 30 minutes, 15 to 30 minutes on average. Can anyone know what summer recreational activity do you see people working where they're changing about every 15 to 30 minutes? Can anyone think of this?
A lifeguard?
It is a lifeguard, which literally is a job where their whole job is using vigilant attention. And this kind of, their behavior, what the pools tend to do is change the lifeguard every 30 minutes. And the reason they're doing that is because their lifeguards are being paid to use their vigilant attention. And after about 30 minutes, theta amplitude tends to increase. And when theta amplitude tends to increase, your likelihood of detecting a person who might be drowning is going to decrease. At the beginning of your shift, your beta amplitude is strong, and so you're likely to notice if there's someone who might be drowning. But after about 30 minutes, your vigilance performance gets worse. Theta amplitude gets higher, beta amplitude gets lower, and so that's why lifeguards switch every 30 minutes or so. I just wanted to, so here's abstracts. These are the actual studies that are cited in the master and his emissary versus about these chicken dual task studies, which are just fascinating, and it's cool that there's multiple studies that support the same idea. In these studies, the chickens basically are it's a dual task, meaning they're having to do two things simultaneously. Look out for food pellets among there's a bunch of distractor things. So food pellets or food grains are small, but there's a bunch of rocks. I think that's what the distractors are. So the animals, one task they're doing is they're looking for food pellets amongst distractors of rocks. So obviously they want to eat the food pellets. They don't want to eat the rocks. So the chicken has to use their attention to find what is the food pellets, what are the food grains, what are the rocks, and I want to eat the food grains, not the rocks. The other task that they're doing is they're having to monitor for a predator. So occasionally when the animals are doing this in the laboratory, the researchers will bring over either a picture of a predator or it'll be actually an actual predator. And so the animal feels like the need to be watching out for potential predators because it knows that sometimes it's seeing the predator in its environment. So it's a little bit on edge, but it wants to eat because it's hungry. And so it's having to do these two tasks simultaneously. Look for food pellets, look for the food grains, simultaneously keep an eye open for a predator. And these are the studies that were provided in the master and his emissary. These studies were cited. And the master and his emissary was making the claim that the right hemisphere of the brain is more important for vigilance. And that claim seems to be supported by these chicken dual task studies. because thinking about the contralateral organization, where each eye, in the case of the chicken, each eye goes to the left hemisphere. The left eye goes to the right hemisphere. The right eye goes to the left hemisphere. And you see, is there an eye that spends more time doing one of these two tasks than the other? And the answer is the right eye in this study is more likely than chance to be the eye that the chicken uses to find the food grains. Whereas the left eye is significantly more likely than chance to be the eye that the chicken is using to monitor for potential threats. So the left eye is connected to the right hemisphere. That's the one that the animal spends the most time using to search out for potential predators in its peripheral vision. This is the evidence that McGilchrist supports the idea that the right hemisphere is dominant for vigilant attention, and that the left hemisphere is dominant for kind of that focal attention, paying attention to small details about the world, trying to find the specific detail of the world. In this case, that would be the food grains. Questions or comments about these vigilance studies?
I have kind of a general question related. Do we know of anything that like affects the beta and theta? So like attention, is that what ADHD medicine functions on, or is it a different mechanism?
I don't know. I would imagine so. I've never read a study where they've where they've compared. I mean, it seems like an obvious study to do, to be honest. But I don't know if it's ever been done. I've never read it. Basically, the question would be: you take like a group of people with ADHD and a group of controls, and then you would have them perform some task that required them to pay attention, and you would predict differences in theta and beta. Based on this, we talked about where'd it go? Theta and beta amplitude. Yeah, you would expect that when people with attention deficit disorder, that they would show higher theta amplitude and smaller beta amplitude, even during even when they'd only been performing the task for 5 minutes. You would expect people with attention deficit to show abnormal theta and beta amplitude. To me, that seems a very reasonable hypothesis, though I just don't know if that study's been done. My guess is it has been done. I just don't know I don't know if it has. So great question. Seems like a potential thing you could maybe do in the master and his emissary paper, potentially, maybe, yeah. Any other questions or comments? Good question there. Anything else? Okay, so I'll talk about this one study, and then, so we won't completely finish chapter 7 today. We'll talk about this one study, and then I think we'll call it a day. So this study, we're getting into a series of studies now in chapter 7. And what all of these studies kind of are arguing, or the cumulative pattern of results in these studies, we're looking here at the back of the brain, so occipital lobe. And what a lot of these studies are interested in is which regions of the visual cortex, which of the regions of the occipital lobe become most enhanced when you are attending to something. Because we've already talked about several visual regions, V1, V2, V4, V5. Those are 4 regions. They're all kind of in the occipital area, and they're all visual regions. That's what the V stands for. The question is, do all of these regions become equally activated? Are they equally enhanced when you're paying attention to something compared to when you're not? How does paying attention to an object influence the activity in all these different occipital visual regions that are here in the occipital lobe in the back of the brain? The pattern of findings, which the cumulative results in the textbook, they all kind of seem to support, for the most part, this idea that you see more attentional modulation in later visual regions. By later, I mean the further away a visual region is from V1 in general, the more attentional modulation you tend to see. So V1, which I'll add, is a region of the brain that has small visual fields, small receptive fields rather. The attentional modulation in V1 is relatively small, probably because it has small receptive fields. In later visual region like V4, and the book also talks about IT, the inferior temporal area. In these areas, they're later in processing. They're areas that are activated after V1. There tends to be more attentional modulation. So when you're paying attention to something, it's more likely to increase your brain's response in V4 or the inferior temporal areas, which are more part of the ventral pathway. You're more likely to see attentional modulation in those later visual areas like V4 and IT compared to V1. V1 is an early visual region in which you don't see tons of activity. So this This right here, this is where they showed activation in this study. People in this study were supposed to attend either to the left visual field in the study, to the right visual. So it's presumably a voluntary attention study. Pay attention to the left side of the world, pay attention to the right side of the world. And we're going to measure what your brain is doing during the preparatory interval, which was 8 seconds long. So this is a fMRI study where they're measuring fMRI responses to during the preparatory interval. So after a cue, but before a target has been presented. And these are the activations that we're seeing. So these are activations, these are the regions of the brain in the right hemisphere that were more activated when you're attending to the left hemifield than when you're attending to the right. So these are the regions of the brain that got bigger when you were attending to the left side of the world compared to when you were attending to the right side of the world. These are the regions of the brain that were bigger when you were attending to the contralateral hemisphere. And this right here is the thalamus. We're going to talk more about that next time. This is part of the thalamus. So it's not technically part of the occipital lobe. So for now, you can ignore this. This is part of the occipital lobe. But I want to point out which brain region is most activated here. So right here is V1. So on this picture, V1 would be about right here. And you notice right here, it'd be V1. V1 is not one of the regions which is activated in this picture. V1 is right there. V1 is right there. V1 is not one of the brain regions that when you're paying attention to something, the activity in V1 is not enhanced compared to when you're not paying attention to something. We see enhancements in the thalamus, which we'll talk about more later. But most of the enhancements we're seeing here, they call VP, which I don't completely know what they mean by VP. I understand that they mean that that is a relatively later visual area than V1 and V2, but this is just not a term that I've heard very much. I understand it's a visual area that's later than V1 and V2. So a later visual area, but they also see some attentional modulation in V4. That's the red area. So you see a lot of the attentional modulation in these later visual regions, but you don't see, so these are just anatomical markings right here. These are not activations right here. These are just anatomical markings. These are the actual activations up here. You don't see much attentional modulation in V1, but you do see attentional modulation in these later brain regions right here, V4 and what they call VP. If it helps, you can kind of think the flow of information once you see something and it goes through the brainstem. The first visual area that is activated is right here, V1. Then you can think of the information as traveling down here to V2, then what they're calling VP, then V4, and then it travels to the temporal lobe, which would be over here. That is the ventral pathway. So V1's up here, the information travels down, and then it travels around into the temporal lobe. Basically, the idea is the further away you are from V1, the more likely, in this study, they showed a lot of activity in VP and V4. There's relatively more attentional modulation in later brain regions than there are earlier brain regions like V1. That's kind of a theme in this chapter. And I guess I kind of wanted to finish chapter 7 today, but it's just too much dense stuff. So we're going to call it a day there. People want to stick around and ask some questions or talk about whatever, go ahead. But unless there are any questions about this right now, I'm going to turn off the recording.